what else do we need to consider to increase solar cell performance? Well, we need to consider what are the components of sunlight. So if you look at this figure 14.9 from the textbook, this shows what the wavelength components are of sunlight and how much irradiance you have at each wavelength for sunlight. Why is this important? Well, for the energy of each photon, if that energy is greater than or equal to the band gap of the semiconductor that makes up that p-n junction, this means that this will provide power to our solar cell. But if the energy of the photon, h mu, is less than the band gap energy of the semiconductor making up the p-n junction, then that energy is insufficient to excite an electron from the valence band up to the conduction band, and it won't create an electron hole pair. So you won't get any power out of those photons if the energy of those photons is less than the band gap. So you want a band gap that matches the energy of the photons that make up this solar spectrum. You don't necessarily want the band gap to be too small, because for this first case, yes, if the photon energy is greater than the band gap, you're providing power, but the most efficient transfer of power is if that photon energy is equal to the band gap energy. If the photon energy is greater than the band gap, then that photon has, some energy more than the band gap. So just by moving the electron from the conduction band to the valence band, that's not using up all the energy of the photon. The excess energy in that photon will be released as heat. So let's look at some band gap energies. For gallium arsenide, that's 1.42 electron volts, and you should have memorized the band gap of silicon. That's 1.12 electron volts. So if we look on this graph, the band gap of gallium arsenide and 1.42 electron volts corresponds to photons of wavelengths with 0.87 microns. So anything longer than a wavelength of 0.87 microns does not provide power to a gallium arsenide solar cell. So all of this part of the solar spectrum provides power to a gallium arsenide solar cell. Silicon has a lower band gap energy, so anything with a wavelength of 1.1 microns or shorter, so this section of the solar spectrum, will provide power to a silicon solar cell. just based on that, on the solar spectrum, you know, if silicon was able to capture the part of the solar spectrum with wavelengths of 1.1 microns or less, that means the maximum efficiency of a silicon p-n junction solar cell would be about 28%. So, you know, based on this graph, the maximum efficiency of a silicon p-n junction solar cell is about 28%. But in silicon solar cells, efficiencies are usually more like 10 to 15% due to non-ideal effects such as reflections, internal resistances, and other effects. And we'll talk a little bit more about that as we go on.